Today's lesson focuses on precipitation reactions. Or I guess all precipitation reactions are double replacement reactions, and writing net-ionic equations. We're going to do a quick overview of electrolytes again because it applies to this very specifically. But does something conduct electricity in solution? Now, several things have to happen if it conducts electricity. There have to be cations in the solution, so some positively charged things, and there have to be some anions in the solution. And essentially these charged particles allow electrons to be carried between really an anode and a cathode, or they allow the flow of electrons to happen through a liquid. But in order for those electrons to be carried by something, there has to be some positive charges available. Strong electrolytes, we kind of had this already. I don't think it was defined this way, but strong electrolytes have 100% dissociation, typically in water. Or what that means is our compound, or our ionic compound, completely dissolves. Okay, it completely dissociates into ions. So instead of being a compound, it dissociates into ions. A weak electrolyte, something like vinegar, acetic acid, does not completely dissociate. So we've kind of talked about reverse reactions a little bit. This would just be an arrow pointing completely to the right, where this would be kind of a small arrow to the right, but a really big arrow back to the left. So a little bit of this goes to the right to make ions, but really most of these ions are forming this back. Okay? Where up here, there's actually going to be a little bit, but a really itty bitty bit. Okay? When we say complete dissociation, we're probably talking in the 99% range, 99.5, but it's quite obvious if it's mostly dissociated, 100%, 99%, or not dissociated. We're going to see these again for some reason. There we go. Alright, so hydration is the process in which an ion is surrounded by water molecules. Okay? If you can kind of think of water, it is OHH. Alright? It is a bent shape. It's a polar molecule. There are electrons, 2 electron pairs over here on the oxygen. So this side of the oxygen, this is the Greek symbol sigma. It just means partial. This side is partially negative. Ooh. And the hydrogen side, if this side's negative, there's got to be a positive to counteract that. The hydrogen side is partially positive. So if we look here, let's say this was, I don't know, potassium iodide. If we put it in water, our iodine is going to become an iodide anion, and our potassium is going to become a potassium ion. Okay? So notice, what side of the waters attack our K+? Is it the O side or the H side? Well, because this positive is touching all the reds, that's the O side. Why is that? Because the O side is partially negative. So really a bunch of water molecules surround our K and essentially rip it off of the big crystal lattice it's a part of. Once that K is ripped off, the next thing that's kind of there on our surface is an I, and again a bunch of water molecules line up, this time the H side of our water, because it's positive, so it's attracted to the negative anion, and it carries this ion off. And eventually we just have a bunch of waters with some positive potassiums floating around and some negative iodides floating around. Here's our water molecule, partial negative, partial positive. Alright, so solubility rules. You need to memorize this table. It is in your textbook, it's table 4.2. But solubility is the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. There are several rules you just have to memorize. We have a lab that we're going to do that at least kind of put stuff, you'll see stuff visually. Hopefully that might help you remember some of this stuff a little better. But compounds containing alkali metals, lithium, sodium, potassium, rubidium, cesium, and the ammonium ion are always soluble. There are no exceptions. Okay? The other thing that have no exceptions would be things like nitrate, bicarbonates, and chlorates. This one, star it, underline it. It is unbelievably important. It probably comes up on the AP test once or twice every year. It will come up once or twice. Halides, chlorides, bromides, iodides are soluble except with silver, lead, and mercury. Okay? So if we had sodium chloride, and we put it in water, we know this dissolves. It's salt. Salt dissolves in water for two reasons. Sodiums are always soluble, and chlorides are also always soluble. If we had something like AgCl, okay, the Ag we know nothing about because it's not an alkali metal, but chlorides are soluble all the time, except with Ag. So if we put silver chloride in water, it would stay as a solid. It would not dissolve. Okay, it would just sink to the bottom, and we would see it as a solid. Sulfates. Sulfates are soluble typically, except with silver, calcium, strontium, barium, mercury, and lead. So you can see the silver, mercury, and lead again. And then the calcium, strontium, and barium are essentially all your alkali metals except for magnesium. So insoluble compounds are things that typically are insoluble. Carbonates, phosphates, chromates, and sulfides are typically insoluble, except with these. Okay? So think of these first. If something has an alkali metal or ammonium, it's soluble, no exceptions, you're done. Hydroxides are insoluble, alright, except with alkali metals, obviously, because they are always soluble, and the barium ion. Okay? And barium is the bottom alkaline earth metal. So up here you have to remember all of them are the top alkaline earth metal. Magnesium is not an exception. And down here, barium, the bottom alkaline earth metal, is the exception. Alright? You can also think about it kind of if you think of your strong acids. Chlorides, bromides, iodides. Okay? They're strong acids, they completely dissociate, and these do most of the time, except with silver, lead, and mercury. If we think of our strong acid, nitric acid, what's true about nitric acid? It always dissociates, no exceptions. What about chloric or perchloric acid? Always, no exceptions. And then sulfates, sulfuric acid is another strong acid. Okay, so sometimes these can actually help you with your solubility rules. It's just the exceptions you have to memorize and be aware of. Alright, so here is kind of a picture of lead iodide forming. There's several colors that you'd be well to memorize. Lead iodide is yellow, a bright yellow, a brilliant yellow. On the AP test, there's a multiple choice section, and typically there will be a question of the 75 that's color related. It might be what are copper ions typically in solution, and they are typically blue. The yellow from lead iodide typically pops up. Nickel ions are typically green. Chromates are usually yellow, but usually there's some sort of kind of a yellowish red or yellowish orange chromates. But there's typically at least one question that's color related, and lead iodide seems to pop up more often than others. It might pop up every 3 or 4 years, but again, if you know lead iodide is yellow, you're probably better off for it. So this is the reaction that's forming if we react lead nitrate with potassium iodide. Okay? And in this reaction, it's a double replacement reaction, which really just says we have a cation with an anion. So we have a positive thing with a negative thing. And we have a positive thing with a negative thing. Okay? So the two things we form, we can't form a positive with a positive. How come? Because it's likes repel. Okay? So this lead, when we put it in water, what's true about nitrates? They're always soluble. So as soon as we put this in water, we really have lead ions floating around in water, and we have nitrates floating around in water, which is kind of symbolized by this picture. So our reactants look like this if we magnified them billions of times. Okay? If we put potassium iodide in water, what's true about K? It's an alkaline earth metal, or an alkali metal, so it completely dissociates. We have K's floating around and I's floating around. Well, the K and the Pb are not going to want to attract at all because they're both positive. But can this K and this nitrate attract? Sure. So this reaction proceeds by making potassium nitrate, and also the lead can be attracted to the iodide. And we make lead iodide. Okay? And these products then look like this picture. What's true about potassium and nitrate? They're always soluble every time. So even though we have them written as making a new compound as a product, Do they look any different on this side than this side? They really don't. We have KO floating around, we have K floating around. We have a nitrate floating around, we have a nitrate floating around. But what about the lead iodide? Over here we have a lead floating around, iodide floating around, but what's forming right down here? We have a crystal forming, or a salt forming, of lead iodide. Okay? Because what's true about iodides? They're soluble, except with silver, lead, ding ding ding, and mercury. Right? So solubility rules are important so that you can predict what's going to happen on the product side of a reaction. We're going to explore this reaction a little bit more. Here's our lead iodide again. Here is what our reaction looks like, probably better represented. Aqueous means that it's dissolved in water. Okay? Anytime you have a nitrate, it's always going to be followed by aqueous because nitrates are always soluble. Sodium iodide will always be soluble. Anytime you have a sodium, it's always going to be aqueous because sodiums are always soluble, no exceptions. Over here we have lead iodide. We have iodides that are usually soluble, except with lead, so it's a solid. And then over here, sodiums are always soluble, nitrates are always soluble, so kind of double whammy. It's going to be aqueous. Yeah. So this is the molecular equation. This is the equation that you're familiar with writing in general chemistry. What we're looking at this year, though, is ionic equations. And ionic equations are basically representations of the pictures we saw on the last slide. So instead of writing lead nitrate as a compound like this, we're really going to write it as Pb plus 2 plus 2 NO3 minuses. Okay? Where does this 2 come from? It's just my subscript going out in front. How come? Because it's aqueous, it's completely dissolved in water. Alright, so my next thing is I have 2 NaIs, 2 sodium iodides. So again, I have 2 Na pluses plus 2 iodides. Okay? And the aqueous just means I'm going to break it up. What's it mean? It means it's dissolved in water, so I'm dissolving my compound into its separate ions. Okay, our next thing is solid. Am I going to break it up? No, because it is actually solid. So I'm going to leave it PbI2. And then again, we have another aqueous compound, so again, we're going to split it up. So we really have 2 Na pluses plus 2 NO3 minus 1s. Okay, so this is an ionic equation. Instead of writing my compounds together, I'm writing ions if they exist. The next part is the net-ionic equation. And the net-ionic equation is based on our ionic equation. So we're going to look for similarities on the left and right hand side. I'm going to change my pen, ink. Alright, so do I see some ions that occur on both sides? Lead is an ion on the left, it's not an ion on the right. I have 2 nitrates on the left, and I have 2 nitrates on the right. So just like on math, if we think of this as an equal sign, I'm going to cross my nitrates out. Okay? I have 2 Na pluses over here. I have 2 Na pluses over here. I have the same thing. They kind of cancel each other out. I have 2 iodides as ions, and now they're in a compound. So what happens is stuff that's similar on the reactant product side gets canceled out, and these things are known as spectator ions. Alright, so spectator ions would be our nitrates and our sodium. So our net ionic equation is simply what is left over. So really what we have left is Pb plus 2 plus 2 iodides yields lead iodide. Okay, and the net ionic equation is really what's happening. We don't care about what's not happening, so the spectators are simply that. They're spectators. If you go to a football game, the football players are playing, the cheerleaders are cheering. What are the spectators doing? Really nothing. They're cheering their team, but they're spectating. They're not part of the action. Okay? Who's part of the action? Lead and iodide are part of the action. What are they doing? They're attracting and becoming lead iodide. Right, so that is net ionic equations. We're going to do one more just as an example, or just kind of a way to, here's kind of a 4-step process to do this. Number 1, write the balanced equation. Number 2, write the ionic equation showing strong electrolytes completely dissociated into cations and anions. Number 3, cancel the spectator ions on both sides of the ionic equation. And then lastly, check that charges and numbers of atoms are balanced in the net-ionic equation. So it's just like a balanced equation, except we're going to make sure our charges are balanced as well as our atoms. So here we go, just another example. Write the net-ionic equation for the reaction of silver nitrate. So silver nitrate. Alright, and we're going to put whether it's aqueous or solid. Nitrates are always soluble, so it's going to be aqueous, with sodium chloride. This is table salt. Sodium is an alkaline metal, it's always soluble. We're done. And we're going to make two things. So silver is with nitrate on the left-hand side, but silver is going to be with chloride on the right-hand side. So chlorides are soluble, except with silver, lead, and mercury, so this is going to form a precipitate. And the other thing we create is sodium nitrate. Alright, what's true about sodium? It's an alkaline metal, they're always soluble, so we're going to write it as aqueous. So this is my molecular equation. Next thing I'm going to write is my ionic equation. So things that are aqueous we're going to split up. So I really have Ag plus NO3 minus plus Na plus Cl minus yields AgCl solid, it stays together, plus Na plus NO3 minus. So our next step is we're going to cancel stuff that's similar on both sides. And if we look on both sides, silver is an ion, silver is in the compound, nitrate, nitrate. So that is a spectator ion. Sodium ion, sodium ion, we have another spectator ion. And then chloride is an ion on the left, but it's part of a compound on the right. So our net ionic equation is simply what's happening. So we have silver ions plus chloride ions are forming silver chloride. And notice at the end I have one silver, one chlorine, one chlorine. Over here if we have +1, -1, we get 0, which is our charge over here, because compounds have a net 0 charge. So that is it for podcast 5.2. Net ionic equations are extremely important in memorizing solubility rules. Solubilities are always double replacement reactions where our partners switch. The cation of one compound switches with the anion of another, or switches with the cation to form up with the anion of the other, and we just have a little hoedown, do-si-do, change your partners, and around you go. So have a great night, and that is it.